Imagine waking up every morning to the sound of rain, and doing that for 2 million years straight. Earth once had the ultimate bad weather day that just refused to end. But this wasn't a drizzle. It was a planet-wide monsoon that rewrote the planet's surface and history. It's hard to picture rain that doesn't stop, not just for a week or a season or even a few centuries, but for a stretch of time so long that entire mountain ranges were born, eroded, and reborn beneath the same relentless downpour. We humans complain about a rainy weekend ruining our barbecue plans. Imagine being a microorganism in the ancient Earth era, floating in a puddle that just wouldn't go away for a couple million years. The skies didn't clear, the ground didn't dry. It was as if the planet had signed a lease with rain itself and couldn't get out of the contract. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation. Quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. But to understand why the sky turned on its sprinkler system for that long, you first need to imagine what the Earth looked like before it started. Picture a young world wrapped in heat and chaos, a molten, smoky sphere that hadn't yet decided what kind of planet it wanted to be. The air was heavy with steam, the land still hot from the planet's birth, and volcanoes were throwing tantrums across the surface. The stage was set for one of the most dramatic weather events in the planet's history. Then came the moment of transformation. The hot, suffocating atmosphere began to cool, just enough for all that trapped water vapor to condense into liquid. What followed was not just rain, it was the great planetary flood, the one that would sculpt the continents, fill the oceans, and permanently change the chemistry of the surface. Raindrops, tiny beads of cosmic consequence began to fall, and they didn't stop. Imagine the sound of that first drop hitting volcanic rock, evaporating instantly. And then thousands more following until the entire planet was shrouded in a roaring, endless storm. The rain was not uniform. In some regions, it would have been a constant sheet of water, a never-ending gray curtain pounding on the rock. In others, it was likely a chaotic blend of thunderstorms, lightning, and steam. The atmosphere was thick enough that light barely pierced through. If you had stood there, it would have felt like existing inside a boiling cloud. You wouldn't have seen the sun for millions of years. Earth was living inside its own foggy pressure cooker. And that unending torrent wasn't just falling. It was transforming. Each drop of water that hit the surface reacted with minerals, cooling the crust, breaking down rock, and releasing new compounds into the runoff. The early Earth's surface wasn't the solid, stable land we know today. It was more like a restless, bubbling mixture of rock, ash, and liquid. Over time, rivers of rainwater carved their way through still-forming terrain, dragging minerals and metals down into low-lying basins. This was the beginning of geology's grand experiment, the birth of erosion on a global scale. But here's where things get even more poetic. That endless rain didn't just shape land. It laid the groundwork for the oceans themselves. Before the deluge, Earth was a fiery desert cloaked in vapor, a place where water existed only as steam. But with this long, unbroken storm, that vapor condensed, cooled, and gathered into pools, lakes, and finally vast basins that became the first seas. The sound of those raindrops was, in a way, the soundtrack of a planet being reborn. For 2 million years, Earth was drenched in its own creation story. The skies were heavy, the ground alive with rushing torrents, and the chemical balance of the surface shifted dramatically. Each storm brought with it more erosion, more minerals released, more gases scrubbed from the air. Slowly, the planet's atmosphere changed from one dominated by carbon dioxide and steam to something cleaner, cooler, and capable of holding liquid water on the surface permanently. Now, imagine what that looked like. The moment when the world's first ocean shimmered beneath the rain, when the first true reflection of the sky appeared on the surface of a cooling world. The sound would have been deafening, the kind of rainfall that blurred the horizon, thunder echoing through thick clouds, lightning constantly flashing over the waves. To the untrained eye, it might have looked like destruction, but it was creation in disguise. And here's the punchline: the irony that nature loves to pull. The same rain that nearly drowned the planet was also what made it habitable. Without that relentless storm, there would be no oceans, no stable atmosphere, and no platform for life to even begin. Earth's longest reign wasn't a tragedy. It was a baptism. When you look at the ocean today, you are staring at the ancient memory of that storm. Every droplet in the sea is a descendant of that first rainfall, a survivor of a million-year tempest. It's humbling to think that our entire biosphere, everything alive today, owes its existence to a sky that once refused to stop crying. So next time you're caught in a drizzle and grumble about the weather, remember this: there was once a time when rain didn't stop for 2 million years. And that's the only reason you have an umbrella to complain under. Long before the rain began, Earth was a fiery toddler. Volcanoes were basically throwing tantrums, spewing carbon dioxide like a cosmic smoker. Temperatures soared, oceans boiled, and the atmosphere was thick enough to make soup jealous. If the Earth we know today is a calm, middle-aged rock with oceans and oxygen and polite weather patterns, the early Earth was its complete opposite. A furious, molten creature still figuring out what solid ground even meant. About 4.5 billion years ago, Earth wasn't the cozy blue marble we love. It was more like a glowing ember floating in space, wrapped in toxic fumes, occasionally bombarded by space debris that hadn't gotten the memo that planet formation was already over. The planet's surface wasn't even a surface in the traditional sense. It was a swirling ocean of magma, churning and heaving like a pot of soup that's perpetually boiling over. Temperatures soared above 2,000 degrees, hot enough to melt rock like butter. There were no continents, no oceans, no sky, just heat, gas, and chaos. Earth wasn't so much a planet as it was a cosmic foundry, forging the building blocks of what would one day become land and water. Volcanoes dominated this landscape. And when I say dominated, I mean they were everywhere. Imagine every horizon lit with the glow of lava fountains, every mountain exploding, and every valley filled with rivers of molten rock. It was the universe's loudest and angriest construction site. These volcanoes were doing more than making noise. They were shaping the atmosphere, one toxic belch at a time. Every eruption spewed out vast quantities of gases: carbon dioxide, sulfur dioxide, water vapor, methane, and ammonia. The air would have been impossible to breathe, even for the hardiest science fiction creature. But that choking haze of gases wasn't random. It was part of a crucial process. Those volcanic emissions were Earth's first attempt at creating an atmosphere. Before that, the planet had barely held on to any gas at all. The solar wind, streams of charged particles from the young, overactive sun, kept blowing lighter elements away. But as the planet's gravity strengthened and its surface cooled just a bit, heavier gases began to stick around. Over time, this built a dense, heavy atmosphere that trapped heat and light. It wasn't a greenhouse yet. It was more like a pressure cooker. And, speaking of pressure, imagine standing on that early Earth, if you could. The air would have felt thick, suffocating, and probably hot enough to cook you instantly. The ground beneath you would shift and crack from heat stress. Even the oceans, if we can call them that, were likely temporary pools of molten silicate mixed with steam. Every inch of the planet was in motion, constantly reshaping itself. In short, Earth was like that friend who insists they're fine while clearly being on fire. Above it all, the sky wasn't blue. It was orange, red, and black, streaked with the glow of magma plumes and dust. There was no sunlight as we know it. The haze of gas and debris filtered it into a dim, smoldering twilight, and the stars were invisible. The only light came from lightning, lava, and the occasional meteorite crashing through the atmosphere like a cosmic exclamation mark. It was beautiful in a terrifying way, a planet mid-evolution, screaming its way into existence. But here's the twist. As violent and unbearable as it was, all that chaos was absolutely necessary. The constant eruptions released the elements that would eventually give rise to oceans, air, and life itself. Water vapor, for instance, was one of the main gases erupting from volcanic vents. It couldn't condense into rain yet because it was far too hot, but it began to accumulate in the atmosphere, thickening the planet's blanket of gas. The future oceans were already floating above the planet, just waiting for their cue to fall. The molten surface also began to cool in patches, forming the first crust. This crust didn't last long before cracking or melting again, but it was a start. Every new layer hardened slightly more than the last, gradually creating pockets of stability. Think of it as the planet's first attempt at growing skin. Eventually, that skin would thicken enough to trap heat beneath and allow the outer surface to become solid rock, though solid is generous. It was more like crust on top of lava soup. Meanwhile, inside Earth, things were equally dramatic. Heavy elements like iron and nickel were sinking toward the center, forming the planet's core. This process released enormous amounts of energy, keeping the surface molten for millions of years. That core, once settled, became a planetary engine that still drives volcanoes and tectonic activity today. So in a way, the Earth's inner fire has never really gone out. It just learned to manage its anger better. As the planet stabilized bit by bit, the thick clouds of gas began to spread more evenly. They formed a blanket around the planet that held in heat but also shielded it from constant asteroid impacts. Over time, the frequency of cosmic collisions decreased, giving Earth a chance to heal. Well, as much as a world covered in lava could heal. The constant volcanic activity was like a chef endlessly tasting their own soup. Add a dash of gas here, release some heat there, stir the magma, repeat for a few 100 million years. By the time this fiery stage began to calm, Earth had developed the perfect storm of ingredients for transformation. There was water vapor, carbon dioxide, and a thick atmosphere, all waiting for the right temperature drop to trigger something spectacular. The molten world was about to meet its first real rain, but it wasn't quite there yet. The pressure was building, literally and metaphorically, as the planet prepared to transition from a world of fire to a world of storms. In the cosmic sense, this was Earth's adolescence, loud, unstable, full of mood swings and dramatic outbursts. But from that chaos came order. From that fury came balance. The angry baby planet was almost ready to calm down, just enough for the sky to finally break, and when it did, the world would never be the same again. With all that volcanic gas, Earth's atmosphere was a choking mix of carbon dioxide and water vapor. Think of it as Earth wearing a greenhouse made of sweat. This steam-laden sky was both a curse and a setup, because that vapor was waiting to fall. At this point in our planet's life, Earth wasn't a solid, friendly sphere so much as a simmering cauldron wrapped in fog. The world had cooled just enough for a crust to begin forming, but not enough to make it comfortable. The air was still thick, dense enough that walking through it would feel like wading through soup. And this soup wasn't made of anything pleasant. It was a mix of volcanic gases, acidic mists, and a colossal amount of water vapor. If you could see it, the atmosphere would look like a swirling, luminous haze, glowing faintly with the reflections of molten rivers below. That steam was the planet's first great paradox. It trapped heat, keeping the surface blisteringly hot, but it also contained the seeds of the cooling to come. The young Earth's atmosphere was essentially one giant sauna turned up to maximum, moist, heavy, and nearly opaque. The sun, though still young and weaker than it is today, could barely pierce the cloud cover. From the surface, daylight was a reddish gloom. From space, Earth would have looked like a smoky marble, not blue but bronze and gray, pulsing faintly with the glow of hidden lava fields. Volcanic outgassing had loaded the atmosphere with carbon dioxide, sulfur dioxide, and methane, gases that love nothing more than trapping heat. The greenhouse effect that followed made our modern climate worries look like a gentle fever. The ground remained far too hot for liquid water, and every droplet that tried to form instantly vaporized. Steam rose endlessly from fissures in the crust, spiraling upward to join the atmospheric blanket, thickening it further. Earth was essentially boiling from the inside out, and the steam refused to escape. The air pressure would have been crushing. The weight of that dense mixture bore down on the surface like an invisible ocean. If a modern human could somehow stand there and survive for more than half a second, their eardrums would burst instantly. The horizon would vanish into a wall of mist. Visibility might have been measured in meters. The entire planet existed in a constant state of twilight. No stars, no blue sky, just a humid, smothering world that couldn't decide whether it wanted to stay molten or start cooling. And yet, for all its brutality, this suffocating atmosphere was performing a critical act of planetary chemistry. The water vapor was constantly cycling, evaporating from the molten surface and condensing higher up in cooler layers of the sky. These constant exchanges helped redistribute heat, creating a global convection system. The Earth's early atmosphere wasn't still. It was restless, alive with swirling storms of steam and gas. Think of it as a slow-motion version of Jupiter's storms, but made of water instead of ammonia, with lightning constantly flashing through the haze. Inside this greenhouse of gas, molecules were dancing. The carbon dioxide trapped heat efficiently, keeping temperatures high enough to maintain volcanic activity, which in turn kept pumping out more gas, a self-sustaining cycle of pressure and heat. But each eruption also added trace elements to the mix: hydrogen, nitrogen, and sulfur compounds that began reacting with one another in ways that would later prove vital. This was the planet's first chemistry lab, and the steam was its solvent. Every droplet carried minerals, salts, and metals in microscopic quantities, turning the air into a thick chemical brew. The great steam blanket wasn't just a cover, it was an incubator. Inside that stifling environment, the foundations of weather and climate were being forged. The constant heat exchange between surface and sky led to enormous temperature gradients. Hot gases surged upward, cooled, and sank again, creating cycles of movement that might have resembled massive, slow tornadoes or endless hurricane systems. The lightning generated by these colossal storm cells would have been frequent and intense, splitting molecules apart and recombining them into new compounds. It was chaos, but creative chaos. Eventually, the relentless cycle of heating and cooling began to tip. Over time, as volcanic activity fluctuated and Earth radiated more heat into space, the upper layers of the atmosphere started to cool faster than the lower ones. This imbalance caused condensation on a global scale, microscopic droplets forming and evaporating again and again, like nature testing the mechanics of rain before committing to the real thing. The clouds grew thicker, darker, and heavier. The great steam blanket was reaching a critical point, too heavy to stay in the sky, too unstable to hold its vaporous form much longer. But before that great fall, the planet lingered in a bizarre in-between state. A world wrapped in permanent fog, with no clear boundaries between air, cloud, and surface. The heat below was still immense, but slowly, imperceptibly, the temperature began to drop toward a tipping point. Within that suffocating atmosphere, something extraordinary was happening. The gases were starting to lose their grip. Water vapor was ready to condense, but it was waiting for the faintest whisper of cooling to begin its descent. Imagine standing there in those final moments before the first rain. The sky would be a luminous orange-gray, thick with boiling clouds. The air would shimmer with heat and haze, the ground hissing beneath your feet as steam escaped through countless vents. Every sound would be muffled, like being inside a giant kettle about to whistle. And then, somewhere, high above the swirling clouds, a single droplet would condense, grow heavy, and fall. It would evaporate before it hit the ground, but it would mark the beginning of something that had never happened before. Precipitation. That first droplet would be joined by others, and slowly, relentlessly, the cycle would cascade into a planet-wide deluge. The great steam blanket, after millions of years of smothering the Earth, would finally give in and release its burden. What followed would be the longest and most transformative rainstorm in planetary history. But for now, the stage was set. The planet was wrapped tight, the air was thick, and the sky was heavy with waiting. The great steam blanket was both prison and promise, a suffocating layer that nearly cooked the young planet alive, but also the womb that would one day birth oceans. It's strange to think that Earth's first great step toward becoming habitable was surviving its own steam bath. But that's how the universe works. It loves to start with extremes. And in that vast, misty cauldron, the story of rain was only just beginning to simmer. Eventually, things cooled just enough for that vapor to condense. And when it did, the heavens didn't just open, they collapsed. It was the longest, wettest, most dramatic weather event in history. Earth went from hellish to hydrologic. For millions of years, the sky had been nothing but a restless sea of vapor, thick enough to block sunlight and heavy enough to feel solid. But somewhere in that ancient storm of gas and heat, balance finally began to shift. The relentless furnace that had defined the young planet started to lose power. Volcanic eruptions became less frequent, the surface cooled ever so slightly, and the upper layers of the atmosphere, those lofty regions where temperatures could finally dip low enough, began to collect water vapor in earnest. At first, the condensation must have seemed insignificant. Microscopic droplets forming high above a world of steam and stone. But soon, those droplets began to merge into larger ones, and larger still. Clouds thickened, darkened, and began to build weight. They were swollen with potential energy. Billions of tons of water waiting for the smallest nudge to fall. And when gravity finally won the argument, it wasn't a drizzle. It was an avalanche from the sky. The first rainfall on Earth would have been apocalyptic. The air was still hot, so the first raindrops evaporated instantly, creating colossal plumes of steam that rose back into the clouds. But as the process continued, it created a powerful feedback loop. The evaporation itself cooled the atmosphere further, allowing even more water to condense. Drop by drop, the balance tipped. Eventually, the rate of condensation outpaced evaporation. And then the deluge began in full force. What followed was a storm unlike anything that has ever happened since. The entire planet was under siege from the sky. Rain fell not for days, not for years, but for millions upon millions of years without pause. Every square inch of Earth was drenched, the sound of falling water echoing across continents that hadn't even formed yet. If you could stand there and somehow survive, you would see rivers appearing out of nothing, carving new paths across still cooling rock, joining into torrents that roared across the landscape. The smell of wet stone, sulfur, and metal would have filled the air. Lightning split the sky in constant, blinding flashes as friction built within the dense, moisture-laden clouds. Thunder rolled endlessly, the sound bouncing off mountain-sized plumes of steam. Every strike of lightning vaporized water, only for that vapor to cool again and fall anew. It was an endless cycle of destruction and renewal. The entire world was wrapped in storms so large they made today's hurricanes look like puddles on a sidewalk. The rain hit the molten plains, cooled them instantly, and cracked them apart. Steam exploded upward in violent jets as the cold water met boiling rock. Each drop that survived the contact ran across the jagged surface, collecting minerals and chemical fragments as it went. These streams carried dissolved metals and salts into forming basins, beginning the chemical foundation for what would eventually become the oceans. The water was acidic, filled with carbon dioxide and volcanic gases, turning it into a corrosive soup that chewed through the newborn crust. Over time, the surface began to change color. What was once glowing red and black turned dull gray and brown as the lava cooled, fractured, and solidified beneath the rain. Entire regions were blanketed by ash from ongoing volcanic eruptions, which the rain then packed into layers of sediment. The relentless weather eroded mountains before they even had a chance to fully rise. In geological terms, Earth was sculpting itself in fast motion, reshaping its entire face under the hammering rhythm of rain. The atmosphere, too, began to transform. Each droplet that fell pulled a tiny bit of carbon dioxide out of the air. This slow cleansing reduced the greenhouse effect, further cooling the planet and reinforcing the downpour. It was like nature found the self-cleaning mode on its planetary settings. Gradually, the air thinned, temperatures dropped, and the clouds, once boiling and heavy, began to settle into patterns of circulation. The great steam blanket from before was being dismantled, piece by piece, replaced by a sky that could finally clear. At the same time, the pressure at the surface began to normalize. The weight of the atmosphere lessened, and visibility improved. For the first time, perhaps in millions of years, a faint sunlight might have pierced the mist in flashes between storms, brief, ghostly glimpses of a new world taking shape. The ground was scarred, yes, but also cooling, stabilizing, and hardening into a foundation that could finally hold water permanently. The longer the rain fell, the deeper the basins became. Cracks in the crust widened into fissures, collecting the runoff from every slope. Pools became lakes. Lakes became seas, and seas merged into vast interconnected bodies of water. The Earth was effectively building its first oceans drop by drop, using nothing but time and gravity. By the time the storm finally began to weaken, there were enormous basins filled with steaming, mineral-rich water stretching across the planet. What's astonishing is that this seemingly violent event wasn't just a moment of destruction. It was the first act of balance. The Earth had been too hot, too unstable, too filled with gas and fury. The rainstorm was the universe's way of pressing the reset button. Every drop cooled the crust, captured carbon, and set the stage for a future atmosphere that could support life. The planet's temper tantrum was ending, and in its wake was peace. Watery, muddy, but peace nonetheless. And let's pause for a moment of humor here. Imagine being one of those first raindrops, tumbling through miles of hot gas toward a sizzling rock. The last thought before vaporizing might have been something like, well, this job has no benefits. Yet, through the collective sacrifice of countless vaporized droplets, the process continued until it finally won. Persistence is one of Earth's earliest virtues. When the clouds at last began to lighten, perhaps after 2 million relentless years, the sound of rainfall softened, the endless rumble gave way to dripping, then quiet. The air cleared enough for sunlight to break through, glinting off newly formed seas. The storms didn't vanish entirely. They merely paused, as though catching their breath after the grand performance. The planet, once a fiery inferno, now shimmered beneath the glow of dawn reflected on water. In that silence after the storm, Earth looked utterly transformed. The crust was cooled, the atmosphere thinned, and the surface, once molten, now held oceans. The planet had survived its baptism. It had gone from a world of fire to a world of water. And for the first time, the sky above and the ground below existed in harmony. It was the end of chaos and the beginning of potential. The clouds had finally broken, and beneath them, a new world waited to begin its story. 2 million years of rain doesn't just fill puddles, it reshapes continents. The downpour eroded mountains, carved valleys, and turned lava plains into oceans. Basically, the planet got a global pressure wash, courtesy of the atmosphere. When the endless storm finally settled into rhythm, Earth was no longer just cooling, it was being sculpted. Every drop that fell carried a microscopic chisel in its chemistry, cutting away at the surface grain by grain. The young planet's crust, still soft and fractured from its molten past, was the perfect canvas for erosion. The rainwater didn't simply land and sit there. It moved. It rushed downhill, gathering speed, carrying with it fragments of rock and ash, carving its signature into the land. The early landscape was chaotic and raw. Imagine towering peaks of black volcanic stone, sharp as knives and brittle from heat, standing beneath thunderclouds that never left. Water cascaded down their slopes, splitting into countless rivulets that tore through the rock, widening cracks into crevices and crevices into canyons. The surface of Earth was undergoing its first true act of geography, the moment when the random chaos of lava flows began to take on shape, contour, and form. As rain fell continuously for millennia, the ground didn't have time to dry. The soil, where it existed, was nothing more than a thin slurry of minerals and mud. Rivers carried this slurry into low-lying areas, where it gathered into vast basins that deepened with every passing storm. These muddy reservoirs were the prototype of oceans, filled with mineral-rich water that hissed and steamed as it spread. The entire surface of the Earth was a dynamic, moving system of erosion and sedimentation, constantly shifting and rebuilding itself. And what those rivers carried was precious. Every grain of sand, every particle of dust, every bit of volcanic ash washed away contained elements that would later become part of the chemistry of life. Iron, silicon, magnesium, calcium, and 100 other ingredients were slowly blended into the watery mix. It was as though the planet had placed itself in a cosmic blender, mixing its crust into the water, setting the stage for something extraordinary yet to come. The process was violent but beautiful. Landslides thundered down slopes as rain undercut cliffs. Entire regions collapsed under the weight of saturation, forming valleys and basins that filled instantly with water. When the rain hit fresh lava, it reacted explosively, fracturing the surface and releasing more minerals into circulation. With every explosion, the air filled with mist, and the mist fell again as rain, feeding the endless loop. Over time, what had been highlands became lowlands. What were once volcanic plains turned into basins deep enough to hold seas. The planet's face was literally melting under the persistence of water. Even the hardest rocks yielded eventually, ground down to sediment. And, as those sediments collected in the depths, they began to form the first layers of sedimentary rock, Earth's earliest attempt at keeping a record of its own history. If you could fast forward through this period in time-lapse, you would see continents appearing and vanishing like slow-motion waves. Water rushing, carving, pooling, and evaporating in an endless cycle of creation and destruction. The rain never let up long enough for stillness. It was perpetual motion, the heartbeat of a transforming planet. You would see rivers snake through glowing lava fields, turning black rock into streaks of mud and stone. You'd watch entire mountain ranges wear down to stumps. It was erosion on an epic scale. Geology's version of a symphony played in thunder and lightning. The constant flow of water also changed the atmosphere in unexpected ways. As the rain dissolved minerals and carried them to the oceans, it drew down enormous quantities of carbon dioxide from the air. This process cooled the climate even further, allowing more water to remain liquid instead of vapor. The more it rained, the more the planet cooled, and the more stable the new hydrological cycle became. What began as chaos was turning into balance, one carved valley at a time. Meanwhile, deep beneath the surface, this vast redistribution of water and sediment began influencing Earth's crust. The weight of the oceans pressed down, while the erosion of highlands lightened the load elsewhere. Slowly, the crust began to flex and shift under the new pressures. This early tectonic stirring would eventually help shape continents and ocean basins more permanently. In a way, the rain didn't just sculpt the surface, it awakened the planet's interior to motion. And it wasn't just a physical transformation, it was a chemical one. The constant churning of water against rock released ions and compounds that began reacting with one another in the depths of the oceans. These interactions laid the foundation for a stable ocean chemistry, creating conditions where future biological reactions could occur. The planetary power wash wasn't only cleaning the surface, it was setting the chemical stage for life itself. From a distance, say, from some alien observer passing by, the young Earth must have looked dazzling. A once fiery sphere now shimmered with silvery storms and dark blue basins. Lightning danced across the surface like electric veins. The entire planet glowed with energy, alive in a way that no lifeless rock could ever be. The rain had transformed it from a world of chaos into a world of patterns, a water world with rivers, seas, and clouds in constant motion. There is something poetic about the idea that destruction and creation are the same force here. Water, the same thing that eroded mountains and stripped the land bare, was also the architect of stability. It smoothed the surface, filled the voids, and created the environments that would one day nurture life. It's the ultimate planetary paradox. The thing that destroys also builds. After millions of years of this relentless downpour, the Earth's sharp edges had softened. The world was no longer a jagged furnace, but a mosaic of water and rock. The air, once choking, was cleaner. The sky, once thick and brown, began to take on shades of gray and blue as the clouds started to thin. The storm was finally running out of energy, leaving behind a planet utterly transformed, washed, sculpted, and reborn. When the last torrents eased and the rumble of thunder grew distant, the silence that followed was monumental. Rivers still flowed, carving their way to the seas, but the roar of the global storm had quieted. The earth had been scoured down to its essence, its rough edges smoothed, its chemistry balanced, its crust cooled and strong. The atmosphere, once a suffocating haze, was now clear enough for light to pass through. In the end, the rain didn't just clean the planet, it gave it character. The valleys and ridges, the oceans and plains, these were its fingerprints, pressed into existence by 2 million years of unstoppable rain. And somewhere, beneath that calm new surface, the story of life was beginning to stir. The storm had ended, but the world it left behind was finally ready to live. All that water had to go somewhere. It pooled in basins and cracks, creating the first true oceans. Earth went from a molten wasteland to something resembling a blue marble. The planet finally earned its Water World badge. For millions of years, rain had battered the planet relentlessly, carving, cooling, and cleansing. Now the water began to gather, collecting in every hollow, every depression, every scar left by the great storms. The once fiery crust was finally cool enough to hold liquid water, and the planet that had once glowed red with lava began to shimmer blue with reflection. Earth's most defining feature, its oceans, had begun to take form. At first, these proto-oceans were nothing like the serene blue expanses we know today. They were hot, dark, and chaotic, simmering with dissolved minerals, metals, and gases. Picture the world's largest cauldrons, each bubbling with chemical energy, releasing steam into the heavy, humid air. The water itself wasn't clear. It was murky, thick with ash, and tinted a ghostly green or brown from the minerals leaching out of the rock below. It wasn't exactly the kind of place you'd want to swim in, unless you were a molecule looking for adventure. The planet's crust, riddled with fractures from its volcanic youth, became a vast drainage network. Water rushed into every crack, widening them into rifts and trenches. In some places, steam vents hissed where rain met magma still lurking close to the surface, creating explosive bursts that spewed minerals and heat into the growing seas. These hydrothermal regions, Earth's first underwater volcanoes, were the furnaces of chemical change. The interaction of water and hot rock began producing a cocktail of compounds that would later become essential for life. As more and more rain fell, the pools joined, the basins overflowed, and the cracks connected, and the planet's geography began to sort itself out into patterns of highs and lows, primitive continents and vast depressions that could hold water permanently. These basins grew deeper as the Earth's crust cooled and contracted. The sheer weight of the water pressing down caused the crust to sink even further, deepening the oceans and stabilizing the planet's surface. Slowly, the water cycle found its rhythm. Steam rose from the hot seas, condensed in the cooler upper atmosphere, and fell again as rain, feeding the system in endless repetition. This circulation didn't just move water, it distributed heat across the globe. The oceans became planetary radiators, moderating temperature extremes and helping to stabilize the young Earth's climate for the first time. The wild pendulum of heat and cold began to swing less violently. The chaos was finding balance. If you could have stood above the Earth at this moment, perhaps watching from orbit, the view would have been breathtaking. Gone was the smoky, angry sphere of molten rock. In its place was a world glistening with clouds and oceans. Blue-gray seas shimmered beneath a sky of drifting mist. Volcanic islands dotted the surface like freckles, their black slopes rising from the steaming waters. Lightning still flashed occasionally, but now it illuminated a calmer world, one that finally looked alive. These first oceans were the most powerful geological agents the planet had ever known. They didn't just sit there. They reshaped everything they touched. Waves crashed against raw volcanic cliffs, grinding them into sand. Currents swirled through the basins, moving sediment and distributing minerals. The chemistry of the water changed hour by hour as it dissolved gases from the atmosphere and reacted with the seafloor. Over time, these reactions began to pull toxins out of the air: ammonia, carbon dioxide, sulfur compounds, trapping them in the oceans or locking them into rocks. One of the most remarkable effects of these newborn seas was their ability to balance Earth's temperature. The oceans acted as a heat sink, absorbing and redistributing energy that would otherwise have cooked the planet. This created a feedback loop. The cooler the surface became, the more water could stay liquid, and the more stable the environment grew. For the first time in its history, Earth could maintain liquid water long term, a requirement for everything that would come next. The chemistry brewing within those depths was extraordinary. With every volcanic vent and every underwater eruption, new minerals and gases were injected into the oceans. Hydrogen sulfide, methane, iron, and nickel, all of it stirred into a global chemical soup. Energy from heat, lightning, and pressure constantly agitated the mix, forcing atoms to form bonds in new and unusual ways. The oceans weren't just passive basins, they were laboratories, running experiments on a scale no human lab could ever match. Meanwhile, sunlight, weak and filtered through the haze of the atmosphere, began to play a role. When the clouds thinned enough, light reached the ocean's surface, triggering further reactions. Some molecules absorbed that light and split apart, creating new pathways for chemistry. The stage was being set for something monumental, though no living cell existed yet to notice. As the seas spread and deepened, they began to reflect more sunlight back into space, giving Earth its first true blue hue. The planet that once glowed with fire now shone with water. It was a transformation so profound that it changed how the Earth interacted with the rest of the solar system. The oceans became the planet's mirror, stabilizing its temperature and softening its climate, allowing the next great leap, the emergence of life, to become possible. And here's the poetic part. The oceans weren't imported from somewhere else. While some comets may have contributed a splash here and there, most of Earth's water came from deep within itself, from steam released by volcanoes, from hydrogen and oxygen locked in minerals, from the very bones of the planet. The rain that fell for millions of years was Earth exhaling its own breath, and the oceans were the condensed form of that breath. The planet had created its own water, its own life-giving element, from its core. By the time the deluge had ended, more than half the planet's surface was underwater. Waves rolled endlessly under the dim young sun, washing against islands that steamed and hissed. The first tides, driven by the pull of the newly formed moon, began to stir the seas, setting water into rhythmic motion. The Earth had entered a new phase of existence, the age of oceans. In that blue expanse, chemistry and geology danced together in quiet preparation and for something unimaginable. But for now, there was peace. The fires had cooled, the rains had ceased, and the world had finally found its reflection. Earth had transformed from molten chaos into a planet of water and potential. It was no longer just a rock orbiting a star. It was a world with oceans shimmering like a jewel in the dark. As the rainwater met the volcanic rock, chemical reactions danced across the crust. Minerals reacted, gases were trapped, and the recipe for life's future kitchen began brewing. The rain wasn't just falling. It was experimenting. Once Earth's surface cooled enough to hold oceans, chemistry took over where geology left off. The planet had been sculpted by water, but now it was being seasoned by it. Rain and rivers didn't simply shape the land. They altered its chemical identity. Every droplet that touched stone became a tiny laboratory, a molecular meeting place where atoms rearranged themselves into new possibilities. The crust of the young Earth was rich in reactive minerals: iron, magnesium, silicon, and aluminum, to name a few. These minerals had been born in the fires of volcanoes and were itching for a partner to bond with. When the first raindrops landed, they didn't just wet the surface, they invaded it, dissolving minerals and carrying their ions into streams and oceans. The result was an invisible storm of chemical exchanges that transformed both the land and the water. One of the most important of these processes was the weathering of silicate rocks. When carbon dioxide from the atmosphere dissolved into rainwater, it formed a weak acid, carbonic acid. This acid reacted with silicate minerals, pulling carbon dioxide out of the air and locking it into carbonate rocks. It was Earth's first natural carbon capture system, one that helped stabilize the planet's climate long before any life existed to care about it. This was chemistry as environmental engineering, billions of years before humans showed up to name it. But the real magic happened in the oceans. As rainwater washed minerals off the land, rivers carried a stew of ions: sodium, calcium, magnesium, chloride, into the seas. Slowly, those waters turned salty. Each element added to the ocean's mix changed how the planet's chemistry behaved. Salts made it easier for electrical charges to move through the water, enabling reactions that would have been impossible in pure, fresh rain. The oceans were turning into electrolytic playgrounds, where energy, matter, and time collaborated on the most complex experiment ever run. Down at the seafloor, the chemistry reached another level of intensity. Rainwater that had percolated through cracks and fissures met magma-heated rock. The result was a seething exchange of minerals and gases. Superheated water gushed back out through vents, rich in metals and compounds like hydrogen sulfide. These underwater cauldrons spewed clouds of hot, mineral-laden fluid into the cooler ocean around them, forming shimmering plumes that settled into layers of black and white mineral deposits. They were, in a sense, Earth's first alchemists, turning raw elements into potential building blocks of life. The oceans became a canvas painted by chemistry. Iron reacted with dissolved oxygen from photochemical processes in the atmosphere, forming rust-red deposits that would one day become banded iron formations, ancient records of early oxidation. Calcium joined with carbonate ions to form primitive limestone. Silica precipitated out in delicate patterns, hardening into the planet's first sedimentary stones. Everywhere water touched rock, new minerals were born and old ones were destroyed. And it wasn't just about rocks. The constant churning of the water and the steady influx of gases from volcanoes created conditions ripe for organic chemistry, the kind that builds molecules of carbon, hydrogen, and oxygen into increasingly complex shapes. Lightning storms striking the surface of the oceans delivered bursts of energy that stitched atoms together. Simple molecules, methane, ammonia, hydrogen cyanide, mixed and mingled in the air and water, forming amino acids, sugars, and other small organic compounds. These weren't alive, not yet, but they were the alphabet of biology beginning to spell its first words. Think of it like this. Earth was running a 2-million-year science experiment, powered by lightning, sunlight, and volcanic heat. The oceans were its beakers, and the crust was its catalyst. Every drop of water, every grain of mineral, and every molecule of gas played a role. Some reactions released heat, others absorbed it. Some trapped carbon, while others released oxygen. The planet was in balance through imbalance, an endless feedback loop of cause and effect that slowly nudged the chemistry of the world toward something astonishingly intricate. Over time, this chemical chaos began to organize itself. Certain reactions produced molecules that were stable and could persist in water, while others vanished almost instantly. The stable ones accumulated, forming concentrated soups in shallow basins and tidal pools. Here, heat from the sun and minerals from the rock worked together to drive further reactions. Complex carbon-based compounds began forming membranes and structures that could trap other molecules inside. They weren't alive, but they were flirting with the idea. The rain, which had once seemed like a destructive force, was now the great conductor of this planetary orchestra. It moved chemicals from land to sea, mixed the layers of the atmosphere with those of the deep, and provided the solvent in which all these reactions occurred. Without it, none of this would have been possible. Rain was the delivery service, the mixing spoon, and the cleaning crew all at once. Even as the storms quieted, the chemistry didn't stop. The balance between the oceans and atmosphere continued to evolve. Some gases, like carbon dioxide and nitrogen, lingered, while others, like hydrogen, escaped into space. Oxygen was still scarce, locked away in minerals, but the seeds of its release had already been planted. The stage was set for future transformations that would eventually fill the sky with breathable air. Looking back, it's tempting to call this era pre-life, but that undersells it. The chemistry of this period wasn't a prelude. It was part of life's story itself. Every rock weathered by rain, every molecule formed in a lightning strike, every mineral dissolved and redeposited was a step toward complexity. The planet was, quite literally, teaching itself how to live. And if Earth had a sense of humor, it might have smirked at its own ingenuity. Here it was, a once molten rock that had cooled enough to run chemical experiments on itself, brewing oceans that would one day brew organisms. The same water that eroded mountains was now learning to build molecules. The same lightning that split the sky was now splitting atoms into life's ingredients. In the quiet that followed the great deluge, as the world settled into cycles of evaporation and rain, something extraordinary was brewing beneath the surface, a chemistry lesson written in water and stone. The rain had stopped falling endlessly, but the reactions it started were far from over. The earth, still steaming, still shifting, was now alive in a new way. Not biologically, but chemically. It had begun to whisper the first words of life. With the carbon dioxide washed out of the air, greenhouse temperatures dropped. Earth went from oven to refrigerator in geologic time. The rain didn't just fill oceans. It rewrote the thermostat settings for the entire planet. For millions of years, the atmosphere had been a suffocating blanket of heat. Carbon dioxide and water vapor trapped sunlight like a thermal prison, keeping the surface hot enough to melt rock. But as the great rains fell and the oceans formed, that suffocating heat trap began to unravel. Bit by bit, raindrops pulled carbon dioxide from the sky, dissolving it and locking it away in the crust below. What followed was one of the most dramatic temperature shifts in planetary history. Earth's first great cool-down. It didn't happen overnight. At first, the climate was a tug-of-war between two forces: volcanoes still belching out carbon dioxide, and oceans greedily absorbing it. Every volcanic eruption tried to reheat the planet, but every rainfall pulled the thermostat lower. The chemistry of weathering took over. When carbon dioxide mixed with water, it formed carbonic acid, mild but persistent, like the planet's own cleaning solution. That acid reacted with rocks, particularly silicates, creating carbonates that settled deep into the forming crust. It was as if the air itself was being scrubbed clean by stone. This wasn't just cooling, it was regulation. The Earth was, without realizing it, inventing climate control. As long as volcanoes pumped gases into the air, the rain kept washing them out. The two processes balanced each other over millions of years, creating a feedback loop that would define the planet's future stability. But during this early phase, the balance tipped dramatically toward cooling. With so much carbon dioxide removed, the greenhouse effect weakened, and temperatures began to plummet. Imagine a world slowly dimming. The once thick, humid atmosphere began to clear. Clouds thinned from dark gray to pale white, sunlight finally reaching the surface with clarity. But the warmth that light carried now escaped more easily into space. The planet began to lose heat faster than it could retain it. Oceans, once steaming like vast kettles, started to calm and cool. The surface temperature dropped, and for the first time the idea of cold existed on Earth. This cooling reshaped everything. Air currents changed direction, winds slowed, and storms that had once raged continuously began to fade. The moisture that once evaporated instantly could now linger as mist, fog or gentle rain. The endless lightning storms that had charged the skies gave way to a quieter, more stable atmosphere. The planet that had been a furnace was learning the art of moderation. At the same time, the cooling oceans began to store gases differently. Cold water can hold more carbon dioxide than warm water. So, as temperatures fell, the oceans absorbed even more of it from the air. The seas became enormous carbon vaults, pulling greenhouse gases out of circulation and locking them away beneath the waves. It was a feedback spiral. The colder the oceans became, the more carbon they absorbed, which made the air even colder still. The planet was effectively air conditioning itself, with no manual override. Geologically speaking, this was a transformation on a grand scale. The crust, once elastic from heat, began to stiffen. The planet's surface cracked less often, volcanic activity slowed, and the land masses that had survived the rain began to harden into something resembling continents. These solidified surfaces reflected more sunlight than molten lava ever could, bouncing energy back into space and reinforcing the cooling. It was the planet's equivalent of swapping out a black t-shirt for a white one on a sunny day. The consequences were enormous. In the upper atmosphere, where water vapor once dominated, clouds of ice crystals began to form. For the first time, snow may have fallen. Not everywhere, but in high-altitude regions or near the pole, where sunlight struggled to reach. Imagine that, a planet that had once been molten and glowing, now experiencing frost. The contrast would have been stunning. Steam still rising from oceans, while patches of glimmering ice appeared on mountain peaks. Earth was finally discovering seasons, or at least their earliest echoes. This cooling also influenced the chemistry of the oceans. As the temperature dropped, minerals began to crystallize and settle to the seafloor, creating distinct layers of sediment. Certain compounds that had dissolved easily in warm water now precipitated out, altering the composition of the seas. The result was a new kind of stability. Oceans that could hold not only heat and gas, but also chemical memory. Layer by layer, the planet was writing its story into stone. The cooling had another, subtler effect. It made energy differences across the planet sharper. The equator remained warmer than the poles, creating the first true gradients in temperature. This difference drove large-scale circulation patterns in both air and sea, moving heat from one region to another. It was the birth of climate zones, a planet beginning to breathe rhythmically, trading warmth and cold between hemispheres. The chaotic storms of the past gave way to structured weather systems, driven not by fury, but by physics. But balance can be a tricky thing. The same processes that stabilized Earth could also push it too far. As carbon dioxide levels dropped further, the planet risked overcooling. Some scientists believe Earth may have flirted with global glaciation, a snowball phase where ice stretched toward the equator, reflecting even more sunlight and plunging temperatures lower. If that happened, it would have been the universe's coldest practical joke, a world that went from molten to frozen in just a few 100 million years. Yet even if the planet froze over temporarily, the cycle would eventually swing back. Volcanoes never truly stopped exhaling. Over eons, they released enough greenhouse gases to tip the balance once more, thawing the ice and restoring equilibrium. The Earth had, perhaps for the first time, discovered the delicate dance between heat and cold, a dance that would repeat endlessly through its history. The most remarkable part of this cooling episode is that it laid the foundation for everything that followed. A stable climate meant a stable ocean. Stable oceans meant reliable chemistry. And reliable chemistry meant that life, still only a twinkle in nature's imagination, would one day have a consistent home to grow in. The planet had gone from chaos to control, from fire to frost, from furnace to fridge. The rain had done more than carve valleys and fill seas. It had quietly rewritten the laws of comfort for an entire planet. It had tuned the atmosphere, balanced the carbon, and set the thermostat to just right. The same process that could have ended the world instead prepared it for life. So, if Earth had a motto carved in its crust, it might read something like this: cooled by chaos, perfected by rain. Because in learning how to shed its heat, our planet learned how to sustain its future. Constant storms meant constant lightning, and lightning loves to play scientist. Those electrical bursts may have sparked the first organic molecules, setting the stage for life. It's like nature's version of cooking with electricity. Even as the great rains faded and Earth's atmosphere began to calm, the skies were anything but silent. Clouds still towered high, dense with moisture and gas. The young planet's atmosphere was rich in ingredients: hydrogen, methane, ammonia, nitrogen, and water vapor, a volatile blend that made every thunderstorm an experiment waiting to happen. Lightning, flashing through those heavy skies, became the universe's most dramatic laboratory equipment. Each bolt of lightning carried an immense amount of energy, enough to superheat the air to temperatures hotter than the surface of the sun. In those microseconds of fury, atoms collided, bonds shattered, and new molecules were born. What was once inert gas could suddenly rearrange itself into something new and surprising. These sparks didn't just light up the sky, they rewrote chemistry. The planet had gone from being shaped by gravity and heat to being shaped by electricity. The atmosphere itself was the perfect testing ground. It contained a mix of simple molecules: carbon dioxide, nitrogen, hydrogen, and traces of methane, all the raw materials needed for complex organic compounds. When lightning tore through these gases, it created energy bursts powerful enough to rearrange their atomic structures. New molecules formed in the blink of an eye: hydrogen cyanide, formaldehyde, and various hydrocarbons. Molecules that, while deadly to us today, were essential precursors to life. These reactions didn't just stay in the sky. Rain carried the newly formed compounds down to the oceans and puddles below, where they mixed into the planet's growing chemical soup. Every storm acted as a massive molecular delivery service, transferring energy and materials between atmosphere and ocean. The result was an Earth soaked not just with water, but with potential. To grasp the scale of this lightning chemistry, imagine millions of bolts striking the surface each day, for centuries upon centuries. Each strike a jolt of creative destruction, breaking some bonds, forming others, churning the atmosphere into a vast reactor. On early Earth, there was no quiet after the storm. The storms were the creative heartbeat of the planet. Modern scientists caught a glimpse of this ancient process in the 1950s when Stanley Miller and Harold Urey recreated it in a lab. They sealed gases like methane, ammonia, and water vapor inside a flask and zapped them with electric sparks. After a few days, the water inside turned pink. When they analyzed it, they found amino acids, the very building blocks of proteins. In essence, they had replayed a scene from Earth's early history. Lightning, it seemed, could do more than scare. It could build. On ancient Earth, this experiment was happening everywhere, all the time. Energy from lightning, volcanic heat, and ultraviolet sunlight constantly interacted with the gases in the atmosphere and the chemicals in the sea. Molecules joined together, split apart, and recombined in an endless dance. Chains of carbon formed rings. Rings linked into chains, and new structures emerged. Amino acids, fatty acids, sugars. The air above and the water below were engaged in a global game of molecular matchmaking. In the shallow pools along coastlines or volcanic islands, these newly forged molecules collected and concentrated. The heat from the sun and the minerals in the rocks acted as catalysts, encouraging even more complex reactions. Some of these compounds began to form membranes, tiny bubbles that could trap waters and chemicals inside. These were not yet living cells, but they were astonishingly close. The line between chemistry and biology was starting to blur. Lightning didn't act alone, of course. It worked in concert with other forces: ultraviolet radiation from the young sun, the heat from hydrothermal vents, and the constant motion of tides. But lightning was special because it provided raw, explosive bursts of energy. It could break stable molecules apart and give them the kick needed to rearrange into something new. It was chaos with purpose, destruction that led to construction. And there's something poetic about that. Every flash of lightning that once tore across those early skies might have contributed to life's beginning. Each storm was a creative frenzy, mixing the raw materials of the planet into more and more intricate forms. The same energy that today knocks out power lines and startles cats may once have assembled the first molecules of life. It's possible that these organic molecules didn't stay put for long. Winds carried them across continents, rains swept them into the seas, and currents distributed them throughout the oceans. Everywhere they went, they encountered new environments: hot vents, cold basins, mineral surfaces, each offering a new chemical challenge. Some of these molecules broke apart, others stuck around, bonding into increasingly complex chains. Out of chaos, patterns began to emerge. Eventually, this constant mixing created the conditions for self-organization. Molecules that could store energy or replicate themselves had a survival advantage, even in a chemical sense. Those that formed stable structures lasted longer, accumulated, and reacted again. What began as random, spark-driven chemistry was slowly becoming a system. The world was no longer just reacting, it was evolving, molecule by molecule. We tend to think of life as something separate from storms, as fragile things hiding from lightning's fury. But on the early Earth, the opposite was true. Lightning was life's midwife, delivering the jolt that transformed lifeless elements into living possibilities. The very thing that now frightens us from behind thunderclouds once wrote the first chapter of biology. Imagine that moment, billions of years ago. A storm rages over a black, steaming sea. Lightning arcs from cloud to water, splitting the sky in blinding flashes. Each strike sends energy cascading through the atmosphere, down into the waves, where new molecules form and drift, fragile but persistent. The air hums with electricity. The sea glows faintly in response. And somewhere, in that glowing mix of water, gas, and energy, the spark doesn't fade. It lingers. It becomes pattern. It becomes potential. Earth didn't just host the storm. It was the storm. A living planet in the making, electrified, experimenting, and learning to assemble itself from its own chaos. In every bolt that split the sky, there was a whisper of creation. Life, beginning not with peace, but with thunder. Scientists didn't just take Earth's word for it, they found the receipts. Ancient rocks hold isotopic fingerprints of heavy rain and ocean formation. Geology is basically Earth's diary, and this chapter was written in soaked ink. The idea that Earth once endured 2 million years of nonstop rain sounds like the kind of myth ancient civilizations might have dreamed up. A cosmic flood story carved into stone tablets. But unlike myths, this one left evidence behind. The proof isn't written in ink or bone. It's buried deep in rock, in chemical signatures and mineral layers that quietly recorded the world's earliest storms. Reading those rocks is like reading a diary that Earth wrote before it even had continents to hold a pen. So, how do scientists reconstruct a time so ancient that no fossils, no shorelines, and no clear land masses remain? They start by following the clues left in the planet's oldest surviving materials. Minerals called zircons. These microscopic crystals, some more than 4 billion years old, are the most faithful record keepers on Earth. Formed in molten rock and durable enough to survive eons of erosion, zircons act like time capsules. Inside them, trapped atoms reveal the chemistry of the world they were born in. When geologists examined these ancient zircons, they found something astonishing. Oxygen isotopes that suggested the crystals had formed in the presence of liquid water. That meant rain and oceans existed far earlier than anyone expected. These weren't just dry volcanic minerals. They carried the unmistakable fingerprints of interaction with water that had weathered rock and seeped into the crust before being melted and reformed into crystal. In essence, zircons are tiny, glittering witnesses to the first great flood. But zircons aren't the only storytellers. The composition of ancient rocks, particularly those found in Western Australia and parts of Canada, also reveals traces of this ancient deluge. Some layers show signs of intense chemical weathering, patterns that only form when rock has been exposed to prolonged rain. The ratios of elements like aluminum to iron and magnesium tell a tale of long, steady erosion rather than violent volcanic activity. It's the kind of weathering you'd expect from endless water falling from the sky, not from random bursts of lava or impact craters. Geologists also turn to isotopes, subtle variations of the same element with different atomic weights. Oxygen, for instance, comes in light and heavy versions, and the balance between them changes depending on how water moves through the environment. Rainwater has a different isotopic signature than seawater, which in turn differs from the water trapped in volcanic minerals. When scientists find ancient rocks with isotope ratios that match modern rainfall, it's like discovering Earth's prehistoric rain gauge. These ratios confirm that liquid water once cycled between atmosphere and surface, falling as rain and evaporating back again. An active hydrological loop, not a one-time splash. Sedimentary rocks, though younger than the first zircons, offer even more tangible clues. Layers of sandstone and shale from billions of years ago show ripples, wave patterns, and grain sorting identical to those seen in modern riverbeds and ocean floors. These are geological fingerprints left by moving water. Some ancient formations even preserve pillow-like structures in basalt, known as pillow lavas, shapes that form only when lava meets water and cools rapidly. Each of these features is a frozen frame of Earth's earliest weather event. Molten rock meeting relentless rain. Scientists can also track the evolution of Earth's atmosphere through the minerals that formed during this period. For instance, certain iron-rich rocks appear banded, alternating between layers of bright red oxidized iron and darker, unoxidized layers. These banded iron formations suggest that as rain fell and oceans spread, oxygen produced by lightning and photochemical reactions began to react with dissolved iron in the seas. Every band marks a chapter in the planet's changing chemistry, a geologic heartbeat pulsing through deep time. And then there's the planetary perspective. Scientists studying meteorites, especially those from Mars and the Moon, use them as cosmic benchmarks. These bodies preserve ancient surfaces similar to what early Earth might have looked like. When researchers compare isotopic compositions between terrestrial rocks and meteorites, they can estimate how much of Earth's water came from within versus how much might have been delivered by space debris. The overwhelming evidence suggests that most of our water wasn't imported by comets. It condensed from the steam in Earth's own atmosphere after volcanic outgassing. The 2-million-year rainstorm was, in effect, Earth sweating itself into oceans. Piecing this story together required detective work worthy of a cosmic Sherlock Holmes. Radiometric dating techniques allowed scientists to assign ages to rocks accurate to within a few million years. No small feat when you're talking about events that happened more than 4 billion years ago. Each isotopic ratio, each mineral inclusion, each erosion pattern became a line in a vast geologic narrative. Where myth speaks in metaphor, these rocks speak in numbers. But perhaps the most persuasive proof of all is consistency. Independent studies across continents, Australia, Greenland, South Africa, have uncovered the same isotopic clues, the same patterns of weathering, the same oxygen signatures. Different rocks, different regions, same story. That level of agreement doesn't happen by coincidence. It's as if the whole planet conspired to leave matching diary entries across its surface, all describing the same event, the rain that never stopped. When you add it all up, the evidence paints a vivid picture. The isotopic data shows that rain fell. The sedimentary layers show that rivers flowed. The minerals show that oceans pooled and chemistry began to churn. Every grain of evidence fits the narrative of a planet transformed by water. Of course, science is cautious by nature. Geologists debate details: how long the rain truly lasted, how deep the oceans were, and how quickly the atmosphere stabilized. But on one point they agree completely. At some point early in its history, Earth transitioned from a world of fire to a world of water, and that transformation left indelible marks in stone. So, when scientists say it rained for 2 million years, they're not exaggerating. They're reading the signatures of ancient storms trapped inside atoms. The Earth may not remember those days consciously, but its rocks do. Each crystal, each isotope, each fossilized ripple in the stone is a line from a chapter written in steam and time. In the end, the rocks don't lie. They don't embellish or forget. They hold the truth of a sky that once collapsed upon itself, of clouds that wept until oceans were born. And in those stones, beneath our feet, lies the planet's oldest confession. I remember the rain. Venus might have had a similar phase, but its rain never reached the ground, evaporating mid-fall. Mars, meanwhile, had a brief flirtation with rain before freezing over. Earth's long storm was rare cosmic luck. When you zoom out from our blue planet and look around the solar system, you realize something almost unsettling. Earth is the odd one out. Among all its rocky neighbors, it's the only one wrapped in liquid water, the only one that learned how to cry, then never stopped. Venus and Mars, our planetary siblings, once held the same potential. Both had atmospheres thick with vapor. Both were shaped by volcanoes, and both likely stood on the brink of rainfall. But while Earth's sky wept oceans into existence, theirs turned those same droplets into tragedy. Start with Venus, the planet that should have been our twin. Similar in size, composition, and distance from the Sun, Venus began with nearly identical ingredients. In its youth, it too may have worn a cloak of clouds heavy with steam. The early Venusian atmosphere was likely dense with carbon dioxide and water vapor, swirling over a molten surface. Lightning cracked through the haze, and for a moment in its infancy, it might have looked like Earth just before the great rains began. But here's where everything diverged. Venus's orbit placed it just a little closer to the Sun, and that little difference meant everything. The sunlight there was intense enough to prevent cooling. As vapor rose and condensed, the droplets that formed high in the atmosphere never survived the fall. The lower atmosphere was simply too hot. Each raindrop evaporated before reaching the ground. A storm that forever hovered. A planet that reigned in theory but never in practice. Imagine standing on the surface of ancient Venus, if you could survive, which you couldn't. The sky above would have glowed a thick golden orange, smeared with endless clouds. Lightning would have flashed in silence, muffled by the density of the air. Somewhere high above, raindrops would form, shimmer and vanish into steam long before touching the molten plains below. It was rain that never landed, water that never became ocean. Venus was a planet that almost cooled, almost lived, but instead it cooked. As the planet's heat intensified, sunlight began to split its water molecules apart. Hydrogen, the lightest element, escaped into space, while oxygen bonded with the surface rocks, oxidizing them into rust-red minerals. The remaining carbon dioxide built up into a runaway greenhouse effect that turned the planet into the inferno we know today. Venus didn't just miss its window, it slammed it shut. The water that could have cooled and balanced the world instead fed the fire that destroyed it. Venus never got its oceans. It drowned in heat. Mars, on the other hand, tells the opposite story, a tale of too little warmth, too much loss. Billions of years ago, young Mars also had an atmosphere thick enough to support rain. Evidence lies etched across its rust-colored surface. Dry river valleys, delta formations, and the ghostly outlines of ancient shorelines. These aren't speculative doodles. They're geological receipts, the signatures of flowing water. At one time, Mars likely had clouds, rain, and even shallow seas. But Mars had a problem. It was small. Small enough that it couldn't hang on to its atmosphere for long. Without a strong magnetic field to protect it, the solar wind stripped its gases away, molecule by molecule. As the air thinned, the pressure dropped, and the boiling point of water plummeted. Rain no longer had a chance to form. What once fell from the sky began to freeze or evaporate instantly. Mars's brief flirtation with rainfall ended in heartbreak, leaving behind nothing but the scars of its short-lived rivers. Today, the Martian surface is a graveyard of ancient rainfall. You can still trace the paths where water once flowed, broad channels cut through craters, branching networks that look like the veins of a desiccated planet. There are minerals, too, like clays and sulfates, that only form in liquid water. They're the whispers of a time when Mars was damp, cloudy, and perhaps even comfortable. But like a candle snuffed too soon, that warmth vanished. Mars went cold and dry, its atmosphere now just a whisper of carbon dioxide swirling above endless dust. What makes Earth's story so remarkable is how delicately it balanced between these two fates. Too close to the sun, and we'd have ended up as Venus. Too hot, too heavy, too doomed. Too far, and we'd have frozen like Mars, brittle, silent, and barren. Earth landed in what scientists romantically call the Goldilocks zone. Not too hot, not too cold, just right. Well, no, just right didn't mean easy. Our planet's 2-million-year rainstorm was part of a razor-thin sequence of events that could have tipped either way. A slightly thicker atmosphere, and the rain might have evaporated before it ever reached the surface. A slightly weaker volcanic output, and the water vapor might have condensed too quickly, plunging the world into permanent ice. Earth walked a tightrope, and against all odds, it didn't fall. Even beyond our solar system, planets like Earth are rare. Astronomers have found exoplanets that may have oceans or clouds, but the exact combination that allowed Earth's hydrological cycle to stabilize, a balanced greenhouse effect, a protective magnetic field, a solid crust, and just the right solar distance, appears to be cosmic luck. It's as though the universe rolled the dice, and our world came up with a winning streak of coincidences. The comparison to Venus and Mars is humbling. One world too hot, one too cold, and between them, a single blue dot that managed to get everything just right. It's easy to forget how fragile that balance is. Our planet's oceans, which now seem eternal, were once a coin toss between vapor and frost. One shift in the sun's brightness, or one change in Earth's early chemistry, and we might have been a story of what could have been, just another dry rock orbiting a star. So when scientists study Venus's acid clouds or Mars's dusty gullies, They're not just exploring alien landscapes, they're reading alternate drafts of our own history. Each of those planets shows what might have happened if Earth had sneezed at the wrong cosmic moment. Venus, the world that rained upwards. Mars, the one that froze mid-sentence. And Earth, the improbable middle child, whose rainfall stayed and sang the oceans into being. In the end, our long storm wasn't just meteorology, it was destiny. Other worlds had clouds too, but only ours learned to let them cry. Imagine 2 million years of nonstop rain now. Cities would vanish, mountains would erode into mud, and humanity would collectively move into submarines. On the bright side, umbrellas would finally get the respect they deserve. It's one of those what-if scenarios that sounds like the premise of a big-budget disaster movie. The day the sky decided never to stop crying. But let us take it seriously for a moment. What would happen if Earth's atmosphere suddenly shifted back to that ancient state, thickened with moisture and primed for an endless downpour? If the rain began tonight and never stopped, not for days, not for centuries, but for 2 million years straight? The first few weeks would seem almost familiar. Streets would flood, rivers would swell, and news outlets would debate whether this was the new normal or just a record-breaking season. Cities would deploy their storm drains and levees, smugly confident in their engineering. But within months, that confidence would drown. Modern infrastructure was never built for permanent precipitation. Reservoirs would overflow. Dams would fail, and entire metropolitan areas would transform into shallow inland seas. Power grids would go first. Water is, after all, a terrible roommate for electricity. Transformers would short out, and entire regions would lose light within days. Communication lines would snap. Internet servers, those delicate heartbeats of modern civilization, would be submerged and silenced. Humanity would wake up in a world gone quiet, where the only sound was the constant hiss of falling water. By the end of the first year, the planet's surface would already look different. Continuous rainfall would erode soil faster than it could regenerate. Hillsides would slump into valleys. Landslides would sweep across continents. The great cities that once stood proud, New York, Tokyo, London, would become submerged ruins. Their skylines reduced to the ghostly outlines of rooftops peaking above gray waves. The world's architecture would dissolve under the endless assault. Stone would crumble. Metal would rust. Concrete would weep itself apart. The atmosphere itself would begin to change too. Constant evaporation and condensation would trap enormous amounts of heat and moisture in circulation. The sky would darken, perpetually overcast, heavy with clouds that never broke. Sunlight would struggle to reach the ground, turning days into dim, twilight hours. The temperature would rise lightly at first as the greenhouse blanket thickened, before cooling dramatically as sunlight faded and the planet's surface radiated heat into space. Eventually, a chill would settle, a damp, bone-deep cold that never lifted. Agriculture would collapse almost immediately. Crops can't thrive without light, and roots can't grow in drowned soil. Fields would turn into lakes, and forests would rot from the bottom up. The great green lungs of the planet would become vast swamps. releasing methane into the air as decomposing vegetation choked on waterlogged ground. The delicate balance of oxygen and carbon dioxide would tilt. Humanity would face not just flooding, but famine. Animals would fare no better. Migratory birds would have nowhere dry to rest. Land mammals would lose their habitats. Even insects, the eternal survivors, would struggle against the constant deluge. The world's ecosystems would retreat upward, onto mountaintops, into treetops, and finally into the few remaining patches of high, dry ground. The oceans would rise, not just from melted glaciers, but from the sheer accumulation of rain. Coastlines would disappear entirely, erased like pencil lines under an eraser of endless water. Within a few centuries, the hydrological cycle would have rewritten the map. Erosion would flatten mountains into broad plains of mud. The Himalayas might still pierce the clouds, but their peaks would be rounded, their glaciers long melted. The Grand Canyon would fill with sediment, smoothing into a shallow depression. Rivers would merge into a single planetary network, flowing endlessly without banks or boundaries. Earth's surface would become a continuous mosaic of shallow seas and deep basins, an echo of its earliest oceanic youth. And humanity? We'd adapt, at least for a while. Floating cities would become the new capitals. Submersible farms might cultivate algae and aquatic plants as our primary food source. We'd breed salt-tolerant crops, build oxygen farms underwater, and live in domes or ships, drifting over the remnants of the continents. Generations would grow up without ever seeing a dry day, and words like sunny or arid would become poetic relics, whispered like myths from a forgotten age. Culturally, rain would stop being a metaphor for melancholy. It would just be the soundtrack of existence. People would measure time by storms, not seasons. Music would imitate the rhythm of water hitting rooftops, and art would shimmer in shades of gray and blue. Even language might evolve around it. New words to describe different tones of rainfall, from the deep drumming of tropical downpours to the whisper of mist against metal. But the long-term consequences would be far darker. With erosion in overdrive, minerals and nutrients would be stripped from the soil and flushed into the sea. The oceans, overloaded with sediment, would grow turbid and acidic. Marine life would collapse as oxygen levels dropped. The water cycle itself could spiral out of control. More evaporation leading to more rain leading to more erosion leading to fewer stable land masses. Eventually, Earth could slip into a permanent water world, where the last remnants of land disappeared beneath the waves. The carbon cycle would also suffer. With vegetation gone and minerals trapped underwater, there would be no efficient way to draw carbon dioxide out of the air. The planet could swing wildly between extreme greenhouse conditions and deep freeze, depending on how much sunlight managed to break through the clouds. It would be a self-sustaining chaos, a climate locked in flux. After 1,000,000 years of ceaseless rain, the planet would look unrecognizable. The continents, as we know them, would be gone, replaced by rolling waves and archipelagos of drowned mountain peaks. Humanity, if still around, would live entirely at sea, perhaps in vast floating habitats, descendants of today's oceanic research stations. Technology would evolve underwater. Architecture would be designed not to defy gravity, but to flow with buoyancy. Our descendants might no longer be land dwellers at all, and yet, somewhere amid all that rain, life would continue. New ecosystems would emerge in the depths. Creatures evolved to thrive in the constant darkness, feeding on chemical energy instead of sunlight. The cycle of adaptation would begin anew. The earth has always been resilient. Even in endless rain, something would find a way to live. So, yes, if the sky decided to rain for 2 million years again, the world we know would vanish. Civilization would dissolve, continents would blur, and the planet would revert to something primal, a blue marble once more. But maybe, just maybe, the Earth would be reminding us of its origins. After all, it's done it before. The last time it rained forever, it made oceans. The next time, who knows? It might make something entirely new. That endless rain was a reset button. It cooled the planet, created oceans, and may have made life possible. It's proof that even catastrophe can be a form of creation, nature's messy way of tidying up. When we think of catastrophe, we tend to picture destruction, something final, something that ends a story. But in the deep past, Earth's greatest catastrophe wasn't an ending at all. The 2-million-year rainstorm, the one that turned a molten planet into a water world, was an act of cosmic housekeeping. It scrubbed, reset, and rebalanced a chaotic young Earth. It's almost poetic. The planet that once burned itself raw learned how to start over, not with fire, but with rain. The lesson begins with humility. If that ancient deluge hadn't happened, the world as we know it would never have formed. There would be no oceans, no atmosphere worth breathing, no gentle blue curve glimmering in sunlight. The event that sounds like annihilation was, in reality, preparation. The flood didn't destroy Earth's potential. It revealed it. It cooled the crust, cleaned the sky, and filled the planet's basins with the very substance that would cradle life. It was nature's way of pressing restart on the planetary operating system. The rain also demonstrated an incredible truth about resilience. Even when conditions seem utterly hostile, nature finds balance. At first, the storm must have seemed endless, a planet wrapped in steam, drowning in its own weather. But within that chaos, a cycle began to form. Rain fell, cooled the surface, condensed, and fell again. Over time, that repetition carved order out of disorder. The Earth, in a sense, learned self-regulation. It discovered that stability could emerge from turbulence. We often imagine the universe as violent and indifferent, and it is. But it also has a strange knack for creating harmony out of disaster. The same four forces that flattened mountains and boiled seas also seeded the chemistry of life. The storm that could have sterilized the world instead created the ingredients for its eventual awakening. The flood wasn't punishment. It was potential, expressed through chaos. That's one of the most profound lessons the ancient rain leaves us. Creation and destruction aren't opposites. They're partners. The forces that dismantle also prepare. Without the pressure of collapse, there is no rebirth. The same principle echoes through everything, from star formation to ecosystems, from evolution to extinction. Planets are born from collisions. stars die to forge heavier elements, and life itself thrives on cycles of death and renewal. The rain that drenched the early earth was one more verse in that universal rhythm. It also reminds us that change doesn't always announce itself as progress. To the hypothetical observer, if one existed back then, Earth would have looked doomed. The endless clouds, the boiling oceans, the violent storms. It would have seemed like destruction incarnate. But behind that apparent ruin was transformation. The molten crust was hardening. Gases were balancing, and chemistry was learning to behave. The planet was quietly becoming habitable, even while it looked uninhabitable. It's a sobering reminder that evolution, whether planetary or biological, rarely looks pretty while it's happening. And here's where the metaphor stretches beautifully into the present. Today, we face our own versions of planetary storms, rising seas, shifting climates, and ecosystems on the brink. To us, these crises feel like endings, but the lesson from that primeval flood suggests something different. Systems under stress can reorganize into new forms. That doesn't mean we should sit back and wait for nature to fix everything. It means that renewal is always possible, even through upheaval. The planet's history is not one of static perfection, but of dynamic recovery. If we view that ancient rain as the first act of balance, then every major shift since, the formation of continents, the rise and fall of ice ages, even the birth and extinction of species, has been a continuation of the same theme: adaptation through disturbance. The Earth is a master of reinvention. It doesn't cling to one version of itself, it evolves. The deluge was just the opening lesson in a curriculum that's still ongoing. Another lesson lies in perspective. When we study those 2 million years of rain, we're peering across a gulf of time so vast that human imagination almost fails. Yet the principle that shaped that event, feedback loops, cause and effect, self-correction, is the same one governing our climate today. When carbon dioxide built up back then, rain scrubbed it out. When temperatures soared, oceans cooled them down. The planet's systems are interconnected, self-aware in a mechanical sort of way. The early Earth didn't survive because it was lucky. It survived because it was built to adapt. We too are products of that adaptability. Every drop of water in our cells, every mineral in our bones, every breath we take comes from the aftermath of that ancient flood. We are, quite literally, children of rain. The oceans that once crashed against bare volcanic stone now cradle entire civilizations. The same water that sculpted the continents runs through our veins. When we drink, we're sipping the same molecules that fell from those ancient clouds billions of years ago. The story of that rain isn't just the story of the planet, it's our origin story. And perhaps the most human lesson in all this is gratitude. The universe didn't owe us a habitable world. There was no guarantee that Earth would balance itself instead of burning like Venus or freezing like Mars. Yet somehow, through a series of violent coincidences, it found equilibrium. The rain, as destructive as it seemed, became a gift, a chaotic act that paved the way for calm. In that way, the 2 million year flood is both a scientific event and a philosophical parable. It teaches that creation doesn't require peace, that beauty can come from turbulence, and that every deluge, literal or metaphorical, carries within it the possibility of renewal. The skies may collapse, but from that collapse can come oceans, life, and understanding. So when we look up at storm clouds today, when thunder rumbles and rain blurs the horizon, it's worth remembering where that sound comes from. It's the echo of the planet's first act of creation through chaos. Every raindrop is a reminder that sometimes the universe builds by breaking. Sometimes the flood isn't the end. It's the beginning rewritten in water. After 2 million years, the last raindrop fell. The clouds parted. Sunlight spilled through, and the world below shimmered blue for the first time. Earth had survived its watery trial, and from that drenched beginning, life would one day rise to tell the story. Imagine that moment. A planet that had known only darkness and storms, now seeing light. For millions of years the skies had been thick with clouds, the air heavy with steam. The sound of falling water was constant, an endless hiss, like the planet itself exhaling. But one day, slowly and almost imperceptibly, the storms began to lose their fury. The thunder softened, the rain grew lighter, and then, in a quiet moment that must have seemed miraculous even to a lifeless world, the downpour stopped. The silence that followed must have been immense. For the first time, the air cleared enough for sunlight to break through in golden shafts. It was light that hadn't touched the surface in geological eternity. Every droplet that had once fallen was now part of something larger. Oceans vast enough to reflect the heavens themselves. The earth, which had spent its youth shrouded in vapor and violence, now revealed its true color. Blue. The transformation wasn't just visual, it was profound on every level. The atmosphere, stripped clean of excess carbon dioxide, was thinner, clearer, and cooler. The violent greenhouse heat had given way to a balanced, breathable calm. The oceans that covered the planet glistened with minerals, shimmering like liquid mirrors beneath the newborn sun. What had once been a fiery, molten landscape was now a world of water and stone, poised on the edge of possibility. On the surface, steam still curled from hot vents where the crust met the sea. Volcanic islands rose from the waves, their black slopes glistening under the returning light. Around them, the ocean boiled gently, releasing the last traces of trapped gas into the air. But the overwhelming mood of the planet had changed. It was no longer angry. It was cooling, stabilizing, breathing. The worst was over. The earth had taken its first calm breath. The end of the great rain wasn't a sudden event. It was a gradual surrender. Clouds thinned layer by layer, revealing fragments of sky between them. Each clearing gave way to another, until eventually the endless gray curtain lifted completely. The stars appeared again for the first time in 2 million years. And when the dawn broke after that first clear night, it illuminated a brand new world. To an observer, had one existed, it would have been breathtaking. The horizon would stretch endlessly, broken only by the outlines of volcanic ridges and newborn continents rising from the sea. The sunlight, striking the waves, would scatter into dazzling hues of silver and turquoise. The air, once suffocating with vapor, would shimmer with mist. And as the wind moved across the surface of the water, the first waves rolled freely without the restraint of torrential rain. Earth, for the first time, had weather that wasn't catastrophic. It had breeze, calm, reflection. The cooling of the planet set the stage for everything that came after. As the rain stopped, the balance of evaporation and condensation finally stabilized. Clouds began to form and disperse in cycles instead of suffocating permanence. The hydrological system, rain, river, ocean, vapor, settled into rhythm. The chaos of creation had given way to pattern. This was the dawn of predictability, the moment when nature began to work in cycles rather than bursts. With stability came opportunity. The oceans that had formed under endless rain began to host increasingly complex chemistry. Molecules dissolved, collided, and reorganized in the calm, shallow waters along volcanic coasts. The heat from geothermal vents provided energy, while minerals offered structure. It was in these quiet, post-storm seas that the groundwork for life was quietly laid. The rain had ended, but its work was far from done. Every drop that had fallen was now part of the great experiment to come. The cooling also allowed new minerals to form, crystals and rocks that could only appear in temperate conditions. These minerals began to build the foundations of continental crust, rising slowly from the depths. The first land masses were born not from fire this time, but from cooling and condensation. The planet that had once been a furnace had become a cradle. The atmosphere, now cleaner and less dense, allowed sunlight to reach the surface without suffocating heat. That light, filtered, gentle, golden, was energy waiting to be harnessed. Photons that once scorched the air now danced harmlessly across the ocean's surface. For the first time, light could reach the depths of shallow seas, energizing the chemistry below. The stage was set for life, though life itself was still just potential. The conditions were perfect. The script had been written. In a sense, the day the sky cleared was Earth's true birthday. Before that, it was a planet in chaos, alive in motion, but not yet alive in essence. Afterward, it was something entirely new, a stable, breathing world with oceans, atmosphere, and light. It had endured its trial by water and emerged transformed. It was finally ready to host the improbable. If there had been a soundtrack to that moment, it wouldn't have been the roar of storms or the crack of thunder. It would have been silence, the quiet hum of a planet cooling, the soft ripple of waves across new oceans, the whisper of wind weaving through the air. It was peace after creation, calm after chaos, the deep exhale after 2 million years of breathless struggle. And though it would still be hundreds of millions of years before life truly took hold, the foundations were there, the chemistry, the energy, the balance. The earth had built its stage and dimmed its fires. The last raindrop, as it fell into the stilling ocean, marked both an ending and a beginning. It's humbling to think that everything alive today, from coral reefs to redwoods to humans themselves, traces its existence back to that moment of clearing. The sunlight that first touched the planet's blue surface was the same light that would one day nourish forests and power thought. The oceans that shimmered beneath it would one day cradle continents and civilizations. When the sky finally cleared, Earth became something extraordinary, a planet that could not only endure but remember. It carried the memory of storms within its waters, the record of creation within its stones. And billions of years later, one of its descendants would look up at a rain cloud, listen to the drops against the window, and wonder where it all began. That moment, the silence after the storm, the first glimmer of blue, was the planet's first sigh of peace. It was the end of chaos, the beginning of life's long, improbable story. And if the earth could speak, it might have whispered to the empty sky above, "I've made it. Let there be calm."